Input term 3 gives output 11.
Watch the scene first. Here in Function Marsh, the math is built right into the world. You'll see the quantities laid out in the physical environment before we ever put a name to them. Consider a path across the water. The stones themselves hold the values 5, 8, 11, and 14. To treat this sequence as a function, we need an input. The input here is strictly the physical step number: step 1, step 2, step 3, and step 4. This set of integer inputs is our domain. When the input is the third step, we look at the corresponding stone. The third term in the sequence is 11, so the function value at input 3 is 11. Treating a sequence as a function simply means mapping an exact integer input, the term number, straight to its corresponding output value in the environment. Sometimes the easiest way to describe a path is by looking at the step right before it. Watch the heron move along the bank. To build a recursive rule, you must pin down the starting point. The first read mark holds a value of 4. We write this as a of 1 equals 4. As the path continues to 7, 10, and 13, each new term increases by 3. We can write this relationship as a of n equals a of n minus 1 plus 3. That notation, a of n minus 1, is just a formal way of saying the previous term. Because we already defined the first term, this rule only applies to the second term and beyond. We record that constraint as n is greater than or equal to 2.
Start at 4, then add 3 for each new term.
Completing our recursive rule. A recursive rule perfectly tracks a step-by-step physical progression, but if you want to find the 100th step, you'd have to calculate the 99 steps that came before it. Let's look at a different trail, marked by shells: 2, 6, 18, and 54. Think about how you might jump straight to any term out there without walking the whole path. Here, the spacing grows exponentially. Instead of adding, each term is multiplied by 3. To build an explicit rule, we take our starting value of 2 and attach our multiplier of 3. But notice the first step hasn't been multiplied by 3 yet. We only multiply when we move to the next step, so we raise the 3 to the power of n minus 1.
So the explicit rule is a of n equals 2 times 3 to the power n minus 1. Checking n equals 1 gives a of 1 equals 2.
Mathematical notation simply records the physical relationships we see in the environment. Every sequence relies on a domain, a set of integer inputs that give us a concrete place to start. The recursive rule tracks the steps from one term to the next, while the explicit rule captures exponential leaps to calculate distant terms instantly. Aligning the physical intervals in a problem with the exact numbers and symbols in these formulas ensures the notation accurately records the relationship you see. As you look at this landscape, which mark in the environment proves the mathematical relationship, and how does the animal action make it true?
The fourth term is 2 times 3 cubed, which is 54.